Hello everyone, today we are gonna do something different. Today we're gonna do a build tutorial. Build tutorials are basically just a little bit edited videos where I show you how you can make stuff what we discussed in the previous episode. So in the previous episode we discussed logic gates and I'm gonna show you how to build some. So the first logic gate is the NOT gate and this one is really simple. We just have lamp, a lever, and a torch, and then a lamp. Now this is our output, this is our input. As you can see, it is inverted. Now the OR gate was also really simple. It was just these two combined, but it will power the other one and we don't want that, so let's just put some repeaters here. That's just how this does work. Works. Now the next gate is called the AND gate, and this is basically just these inputs inverted, then I get OR together, and then it gets inverted again. Why does this work? Well, this torch has to turn on. That means this dust has to turn off. And this dust only turns off when this torch is off, and this torch is off. And these torches are off when these inputs are on. So now these torches are off, so this dust can turn off. And this torch will turn on, so the output will be on. Now we can make the XOR gate. And we have a few designs for that. We have a lot of designs for those. So first up we have this design. Wait. Let's step you just close. So we had this design, and I forgot to give some explanation about this. So let me tell you how this thing works. Basically, when this block gets hard powered by this repeater, this dust turns off and this dust turns on, and this dust will go to the other comparator. That comparator will hard power this block, and it will turn on this lamp. But when both are on, they will cancel their own sides, and this means the output doesn't turn on. So if one is on, the signal can go to the other side and this one doesn't get cancelled, so it can flow through. But if they're both on, the output will be off because they both get cancelled. And of course, if they're both off, there's no output to go through, so it just turns off. Then we had this design. Which works exactly the same. So right here are just 14 minus 14, which is not possible, but here are just 13 minus 11, which is possible. And I told you guys it gives a low signal strength, but as you can see, it gives off a signal strength of 2. That's really low. And this one, 14. That's way better. So that's why I almost never use this design. So the next design I showed you guys was with the torches. I think it was like this. I think it was like this, I'm not sure. Yes, Yes, it was like this. I'm not sure how this one works. But we can inspect it like we did with the AND gate, of course. Maybe I will learn something today. So for this output to be on, we want one of these two torches to be on. These are on when this one is... Alright, let's just say we want this one to be on. So this one is on when this one is on. So this one is on, it will go there. But when this other one is on, it will like cancel it and it will turn off. And if we alright, so that's kinda how it works, I think. Now the last design we made was really big. And I also forgot to give some explanation on that one. So we had an OR gate. This basically does the same, but if both inputs are on, the output is still on and it should be off in that case. So then we want to detect when both are on. We do that with an AND gate. Now if we look, we can detect when they're both on. Let's just combine these two so that we know what. Here's a little bridge. So now we know when one input is on. So we can see that one input is on and they're not both on. Same for this. Wait. I connected them to the same one. So now one input is on and this one is not on. When they're both on, this one will also turn on. And basically what we want is this one to be on, but this one to be off, because we want one input to be on, but not both. So we can invert this one, just remove this torch. And now, if we look at these two, we can see that when one input is on, they're both on. If none is on, then one of them is off, and if they're both on, then also this one is also off. So we want these two to be both on, and we can do that with another AND gate at the end. This is exactly what I showed you guys yesterday. So right now these are both on, and this AND gate says, hey, they're both on. And we don't want that, so it tells the next AND gate, this input should be off. So the output will be off, because this guy detects that both inputs are on. That's how this XNOR gate works. And how to build it, of course. Alright, the next gates are the same but inverted, of course. So we got the NOR gate. So that's just an OR gate, but then the output will just be inverted, like this. So now the output is only on when all the inputs are off. The next gate is the NAND gate. And that's just an AND gate, of course, with the NOT gate at the end. So we got a NOT gate at the end here. But of course, a double inversion can just be removed and we'll get the same result. And now the output will only turn off when both inputs are on. So this one is on when all the inputs are 0. So if one input is on, the output will be off. And this one is on when one input is 0. So if they're both 1, the output will be off. Now for the XNOR gate, we'll just pick an we'll just take an XNOR gate. Let's just take this design. And with a torch at the end. And this is our XNOR gate. So this guy will only be on when one input. This guy will only be off when one input is on. So that's how you build these logic gates.